Today is the last day of summer school on algorithm. In this first session, we are going to continue the talk on stable matching by Professor Meghana Nasre. I welcome Professor to give the talk. Over to you, ma'am.
Yeah, thank you, Abiba, for the introduction. And yeah, so we will continue our discussion from where we left yesterday. I will recall the models that we had discussed. So we had set up these three models or settings. So the classical setting of the stable marriage problem, if you recall, is where applicants have we call them men and women, and men and women both have strict and complete lists, and the goal is to compute a stable matching in that. And we have already seen the Gale and Shapley algorithm. Then we described variation 1, where strict lists and incomplete lists are there. We saw that in that setting, all stable matchings, we did not see a proof, but we said that all stable matchings have the same size. And therefore, the goal is to ask, is there a matching which is of larger size and is optimal? And in variation 2, we have strict lists. Sorry, I should not say strict. I should this is a typo here. It should be yeah, it should be incomplete lists and ties, because strict and ties is a contradiction. So incomplete lists and ties, and we want to compute the largest stable matching. So we have already seen this setup where we have incomplete lists and ties. We are focusing on the case where only the B side has ties, like shown here. So this is called the women, and the women only have ties. And we have seen examples where there are multiple stable matchings of different sizes, and the natural goal is to compute the largest size stable matching. Computing any stable matching is easy. You can easily do that by breaking ties arbitrarily and running the Gale and Shapley algorithm. However, computing largest size stable matchings is NP hard even under restricted setting. So we said that we also saw the state of affairs for this problem, and we said that we are going to focus on this variant, which is okay. So the Kiraya's algorithm, which gives us a 0.66 approximation to the maximum size stable matching, and we also set up our algorithm in yesterday's class. So we said the Kiraya's algorithm, we are going to, I repeat, we are going to do it only for the case where B side has ties. So we said break ties arbitrarily in whichever way you want. Execute the Gale and Shapley algorithm. It is guaranteed to give you a stable matching for the way you have broken the ties, and that will also remain stable for the tied instance. And now unmatched A's propose with increased priority. So we think of them as starred men or starred agents, and they propose when an unmatched man proposes to a woman. The woman looks at her matched partner. If the matched partner is without increased priority but in a tie with the current proposing person, then she rejects the current partner and accepts the proposal. If it is a strict preference, that is, she is matched to a strictly better partner, then the woman does not change her preference. So so we say this by saying that B uses increased priority for breaking ties alone. So she never jumps her priority and accepts somebody who is weaker in preference over the current. So she never changes her priority. That is important. Therefore, we are ensuring that stability is never violated. The goal that we left is we want to show that this is a good approximation to the maximum size weakly stable matching in the instance. So we ran this, we had this execution in action. So we said, if this is the instance, we break the ties arbitrarily, but we break it unfavorably for us. That is, we know that if we break it as A2, A1, we will get a maximum size stable matching, but we break it in the bad way, that is A1, A2. Therefore, Gale and Shapley gives us the matching, which is just A1, B1. But then A2 star proposes to B1, and B1 now looks at the current partner and says that, okay, I have A1, I will accept A2 star because A2 star is a higher priority man, and also that I was tied with A2 and I was tied with A1 and A2 were tied in my preference list. So that is why it is accepting it. And once it accepts it, A1 becomes free. Therefore, A1 goes ahead and it has not even completed its preference list. Therefore, it will go and propose to B2, which will accept it because it is not something that it is not matched to somebody. So this is the algorithm. So before I proceed, are there any questions about the algorithm? Okay. So this is the matching, and our goal is to show that the size of the matching is good. That is, it is a good approximation to the maximum cardinality stable matching in the instance. And the way we are going to show this is by showing that there are no short augmenting paths with respect to the current matching. So what do I mean by short augmenting paths? So before that, I have to talk about what is augmenting paths. And this also we kind of set it up in yesterday's class. So we said this is any bipartite graph. The red edges are matched edges. You don't have to worry about preferences. It's just a bipartite graph. You can think about the bipartite graph without preferences. So if the red edges are matched edges and the gray edges are the edges which are there in the graph, of course the red edges are also there in the graph, but they are matched, then we say that a path which alternates between matched and unmatched edges is an alternating path. And there are several alternating paths. For example, a path which is A5, B1, A3 is an alternating path. Similarly, somebody had pointed out that there is a 3-length alternating path, which is the following: B5, A3, B1, A2. This is a interesting path because we see that if we switch the matched versus unmatched edges along this path, then we get a larger sized matching. And this path has a special name which is called as an augmenting path. And an augmenting path is an alternating path with both the endpoints free with respect to the matching. So both alternating and augmenting paths are always described with respect to the given matching. The given matching can as well be empty. So what we observed is that augmenting paths always have odd number of edges because of the way they will be having some number of edges which is of the form 2k plus 1, where there are k matched edges and k plus 1 unmatched edges. And the important point to note is that whenever you have an augmenting path, the augmenting paths can be short, long, or anything. If you use one augmenting path and modify the matching, or it is called as augmenting the matching, the size of the matching increases by 1. So irrespective of the length of the path, the size of the matching increases by only 1. The path may be long, therefore it may change lot of edges, but still it increases the size of the matching by exactly 1. And if you do not have a one length augmenting path, then it is called a maximal matching. That is a matching which cannot be improved by simply adding edges in terms of its size. So what we will show is that whenever you do not have short augmenting paths, we are close in terms of size to the maximum cardinality matching. This has nothing to do with preferences. This is a general claim which holds true in graphs without preferences. Also in general graphs, it does not require bipartiteness underlying it. So that is not required. But what we will show is that for our proof, it suffices to have to prove that the matching that we produce does not have 1 or 3 length augmenting paths. Yeah, so I'll pause here. Is there any question or comment here? Okay. Okay, so I would like you to participate and tell me. So I have this matching M, which is any matching in a graph. Remember that we are not dealing with preferences for the moment, and M star is a maximum cardinality matching. So let's for the moment assume that M is not a maximum matching. So one thing that I want to ask is everybody familiar with the symmetric difference notion? That is the symmetric difference of two sets or the symmetric difference of two matchings. Anybody has seen it? Can somebody tell me what is the symmetric difference of two sets first of all, and then we can extend it to symmetric difference of two matchings.
Basically, symmetric difference of M and M star will be basically those edges which belongs to exactly one of them.
Correct. So this is the definition of the symmetric difference with respect to two sets. M and M prime are in fact subsets of the edge set, so it applies to that. So it contains the set of edges that belongs to exactly one of the matchings. So if the edge does not belong to any of the matchings, we just discard it. If it belongs to both the matchings, we discard it. So now I want you to tell me that if I just construct the graph containing the edges which belong to the symmetric difference of the two matchings M and M star, what kind of graph do we get?
Basically path or even cycle.
Good. So we get some paths or even cycles, and these are M star alternating paths and cycles, right? So may I know who is answering? I don't see the person who is speaking.
Ma'am, I am Sachin, a research scholar in Department of Mathematics, IIT Delhi. I am working with Professor B.S. Panda.
Okay, very nice. Okay, so
thank you, ma'am.
Yeah, thanks. So you are aware of what is the symmetric difference, and you know that there can be symmetric the graph on the symmetric difference of M and M star will just contain alternating paths and cycles. Now, yeah, so just hold on for a moment. Let others also answer. So if you have M star, okay, so what happens when you have these paths? So people who are possibly seeing it for the first time, I just want to know what happens when you have these paths and cycles. How do these paths and cycles affect this matching, or how do you change from M to get better matchings, better sized matchings? Anybody? So I just want to get a sense whether people have seen it, or people are aware of this and therefore they find it very slow, or what is it, or they don't know. That is what I don't understand. So somebody who okay. I'm just going to pick out people, and I hope they don't feel that I'm putting them on spot. Ishwaran, right? You were interacting yesterday. So Ishwaran, have you seen this stuff, and do you see what will happen if we have this M symmetric difference M star?
No, I would not be able to answer that, ma'am.
Okay. So are you unable to visualize, or what is it?
No, actually, this area is new for me, so I'm trying to assimilate. I'm in a phase of assimilation rather than trying to.
Okay. Okay. So I think except for Sachin, right? You answered the question. So what I want to say is that if you have some matching, let's draw the matching M with blue edges and M star with black edges. And we are saying that we are only going to draw the edges of M XOR M star, or M symmetric difference M star. So I'm going to write it here, M symmetric difference M star. This is the notation that is used for symmetric difference. And if we are just constructing the edges of M symmetric difference M star, then we are going to get a structure which is of the following form. So the M edges we are going to draw using blue. So now let's say this pair of vertices is AB, which are matched with respect to M. Then what can happen on B? Can you have another edge which is blue colored? You cannot have another edge which is blue colored, but you can have an edge of M star. So for example, M star M star B may be matched to some other vertex. Maybe it is matched to some other vertex A prime. So this is how this can go ahead. Now let's ask about what happens with A prime. So A prime may not have an M edge incident on it, or it may be matched to somebody else. Remember that if A prime were matched to the same vertex in both M and M prime, then we would not be having that edge, because we are only constructing edges in the symmetric difference. So how can this end? So we can keep drawing this edge which is B prime, which is like this. Further ahead we can go. Is there a different way I can complete this picture? Is there something else that can happen? So I can keep continuing and I can draw A double prime and then again say that there is another edge and this path continues. But is there any other way I can stop? So I can always stop at any point. I can say that this vertex is unmatched in the matching that I am interested in. For example, B double prime does not have a black edge incident on it. Then I stop. But what else can happen? Can somebody tell me? So the thing that can happen is that B double prime's matched partner in the matching M star, which is the black matching, can itself be A, and therefore I can connect this B double prime to A in this following manner. That is this, and we can get a cycle. So we can get a cycle which is called as an alternating cycle. We can also get a path which we were drawing. For example, we can have a path like this, which has equal number of M and M prime, M star edges. And I'm just going to keep it short because I will just draw it to length, but it can as well be any even length, or it can have the following structure. That is, it has more number of M edges, the M star edges, versus less number of M edges. It can be a structure like this. So this is called as an odd length path, which is again an alternating path. Why do I say that there is no other structure? What else could have happened? I mean, if you give yourself all possibilities, I could have had a structure which I could conceive a structure which is like this. That is, it has more M edges versus, I mean, okay, so this should be a black edge. So why does this structure not happen, or why are we saying this structure does not happen? Anybody? Yeah, maybe Sachin, if you are aware, or you can think of it. Yeah, so.
Ma'am, then if we change this blue edges with black, basically if we change alternate the edges between M and M star, then cardinality of M will be greater. Basically, we are basically this black edge is for M, right?
Black edge is for M star. M star is a maximum cardinality matching. M is some matching, right?
So then if we in M star, if we take these blue edges instead of black, then we will get cardinality 1 greater than the maximum size.
Correct. So what is wrong with that? We'll get one.
So size, we'll get a matching of size larger than the maximum.
Correct. So we have assumed that this M star that we have taken is a maximum cardinality matching. So you cannot increase M star. So in fact, with respect to M star, there are no augmenting paths. This is an augmenting path. This path that we have drawn here is an augmenting path with respect to M star, versus this path is an augmenting path with respect to M. So the M augmenting paths are possible, or just M alternating paths are possible, which are containing the same number of M and M star edges, or there can be M alternating cycles which also do not change the cardinality of M or M star. So if you look at the symmetric difference, there are only these structures, and if M star is a maximum matching, then this structure that we have drawn here on the last part cannot occur. This is the learning that we have. So is it clear to people who have not possibly seen the is this thing, or is there any question about this? Okay, as I said yesterday, I mean, it's better to ask questions and get it clarified rather than, because it's most likely that there is something simple that you don't understand, rather than assuming that you have not understood something very big. Okay. Okay, so now that we know that the symmetric difference has a particular structure, and if M and M star are far apart by T size, that is T is the difference in size of M star and M. Remember, M star is a maximum matching, so size of M star is greater than or equal to the size of M. In particular, if M is also a maximum matching, T can be 0. But in general, T is a positive integer if M is any arbitrary matching. Then we know that in the symmetric difference of Mx or M star, we have T augmenting paths with respect to M. The augmenting path is a path which has more number of M star edges versus less number of M edges, right? And each augmenting path is going to give us a size increase by 1. So this is good. So we have exactly T augmenting paths with respect to M. However, what we will assume now is that assume that M does not have short augmenting paths. So in my pictures that I had drawn earlier, I had drawn a 3 length augmenting path. So 3 is considered short. We can define what is short for us, but we can say that 1 and 3 are short augmenting paths, whereas anything above 3 is long augmenting paths. So if you believe this, that okay, this is what is our definition, then if let's assume that the shortest augmenting path is of length 2k plus 1, that is up to 2k minus 1, there are no augmenting paths of this length 1, 3, 5, 7 up to 2k minus 1, so for some fixed integer k. So what do we want to claim now? That if this is the condition, that is it does not have short augmenting paths, then the number of augmenting paths itself is going to be upper bounded. That is the number of augmenting paths. Remember, T is the number of augmenting paths with respect to M. T itself is upper bounded by the number of edges in M divided by K. Now, where did I get this from? How did I derive this? That the number of augmenting paths is upper bounded by M over K. So, I mean, just intuitively, we have a set of edges. We have augmenting paths with respect to that, and all augmenting paths are long, right? So if you have large number, if you have a collection of things and it is just saying that if you group them into large number of things, then you are going to get small number of groups. That's all we are saying. But how do you formalize this, and how did I get this cardinality of M over K? Any thoughts?
Maybe probably I missed something. What is K here?
Oh, so I said that the shortest augmenting path with respect to M is at least 2k plus 1. So K is any fixed integer. And I'm just saying, so if you fix K equal to 1, then you will get that it is of length 5, right?
Okay.
Sorry, 3. So the shortest augmenting path is of length at least 3. If you fix K is equal to 1, then the shortest augmenting path is of length 2 plus 1, which is 3. If you fix it to be 2, then you will get it 5 and so on. So you fix an integer and you say that the shortest augmenting path is at least 2k plus 1. Is that clear, Pradisha?
Yes.
Yeah,
I
sure.
missed the definition.
Okay. So now, how did I claim that I get T is upper bounded by M over K? So note that, I mean, augmenting paths are not constructed in the thin air. Augmenting paths are constructed out of the matched edges and unmatched edges, right? So every augmenting path is going to consume matched edges. Consume in the sense use matched edges, and these are vertex disjoint, therefore edge disjoint augmenting paths. So now if you have cardinality of many M edges, that is there are cardinality of many such matched edges of M, each augmenting path is going to use up some edges. So let's take one augmenting path. Every augmenting path is of length at least 2k plus 1. So it uses k matched edges and then has k plus 1 unmatched edges. That is where the 2k plus 1 is coming, right? So it has k matched edges and k plus 1 unmatched edges. So it uses k matched edges. So therefore, you can think of taking the matched edges, dividing them into groups, each consuming k number of edges. So if you consume k number of edges, you can have at most m over k groups or m over k things that are left, m over k groups that are there. Each of these groups can form an augmenting path, and therefore the total number of augmenting paths is upper bounded by m over k. Is this clear? Is it okay? Are there questions? So okay, I hear so much silence in contrast to yesterday that I don't know. Okay, so if there is a question, please interrupt me. So now we just put things together. That is T, we know that m star minus m is equal to T, or in fact m star is equal to m plus T. But T is upper bounded. T is upper bounded by m over k. And therefore we know that m star is less than or upper bounded by k plus 1 over k times m, the cardinality of m. But we want it in the other way. That is, we want that, we want to say in fact that m is greater than or equal to k over k plus 1 times m star. That is, we say that m is at least k over k plus 1 times the cardinality of m star, which means that it is k over k plus 1 approximation to m star. So what this, just to recap, what this tells us at a high level is that as you take away the matching and rob it of short augmenting paths, then it is going to be a closer and closer approximation to the maximum cardinality matching. So if you put k is equal to 1, you will get a maximal matching. Any maximal matching is at least half the size of the maximum cardinality matching. Any matching that does not have 1 and 3 length augmenting paths will be a 2 over 3 approximation to the maximum cardinality matching, and so on. And that is what we are going to use. So anything that people want to comment or ask?
I have a question. So does it mean that you will never be very far away from the optimal situation, right?
Exactly. So very far, what do you mean by very far?
So I'm saying 50% is a worst case scenario. Therefore, you're probably at 75% half the time. I'm just conjecturing it.
Yeah, so 50% is easy to get because as soon as you get maximality, you get 50%. Yeah, you are right in that sense that you get 50% almost free.
Okay.
But then, as I told you in yesterday's this thing, that the lower bound on things is just like 0.9, right? It says that there is no 0.9 approximation. Yeah. So we want to reach there. We want to reach as close as possible. And the challenge is also practical and and theoretical. In practice also, if you settle for 50%, people will be quite unhappy.
Yes.
Yeah. Okay. So yeah, is there any other question? So as I said, this proof has nothing to do with matchings with preferences, not even with bipartite matchings. This proof holds for general graphs. And if you have a matching in any graph which does not have short augmenting paths, or the longest augmenting path, the shortest augmenting path is of length 2k plus at least 2k plus 1, then it is a k over k plus 1 approximation to the maximum matching. So this is a well-known fact, and this is what we will be using in the analysis of our algorithm. Okay, so back to our Kiraya's algorithm that we have seen, and we have already recalled it. And so now we need to argue about the size of the output. But what we have now understood is there's no need to do too much work. We just want to say that the matching does not have short augmenting paths. And just by the fact that it is a maximal matching, because stable matchings are maximal, therefore it cannot have a one length augmenting path. So the only hard work that we have to do is there are no 3 length augmenting paths with respect to the symmetric difference of our output and the largest size stable matching in the instance. That's all we want to show. Then it will be a good approximation to the maximum size stable matching in the instance. So this is our plan, that is we will show that there is no 3 length augmenting path with respect to the matching that we have produced. Okay, so any doubt or anything? Okay, so we will make some observations about Kiraya's algorithm. So let us say that a woman was unmatched at the end of the algorithm, right? So how did our algorithm work? It is written on the slide above. It breaks ties arbitrarily. It executes Gale and Shapley algorithm, and then unmatched is proposed with increased priority. So after doing all of this, if the woman is unmatched, then she never received a proposal, because if a woman was unmatched at any point and she receives a proposal, she will immediately accept it. So if a woman if a woman is unmatched at the end of it, she has never received any proposal from anybody. This is a simple observation, but it is useful. The second is, if a man is unmatched at the end of the algorithm, the man must have proposed with increased priority and exhausted its list completely and still not got matched. And that is the reason that the man remains unmatched at the end of our algorithm, because we did this step of increasing the priority. So both these observations are simple but useful. Okay, so after doing all of this, assume that still there is a 3-length augmenting path. That is, the path looks like this. The gray edges are in fact our edges. The gray edges are the maximum cardinality stable matching edges, and the red edge is our edge. That is why it is called an augmenting path with respect to the matching that we have produced. So whatever I am calling as M algo is the output of our algorithm, and this is the matching that we produce, and there is an augmenting path with respect to it. So we want to show that such a structure cannot exist, right? So what is it that we can contradict? I mean, how will you contradict, or what is it that we can contradict? Is there any idea? So remember that both these matchings are stable. That is, I mean, the edges, the gray edges, which are A1, B1, A2, B2, which are a part of the maximum cardinality stable matching, are forming a stable matching. Similarly, A2, B1 is also a part of a stable matching. So the only handle that we seem to have is somehow contradict stability. How does one contradict stability?
By adding the edge that is left out.
I didn't understand. Can you repeat? Adding the edge that is left out. How do see? How does one contradict stability? That is the question. But which
okay,
edge should
I mean, for example, let's say the matching is A to B1.
Okay, it is our matching. Okay, yeah.
Yeah. So if you basically okay, A to B1. You can contradict stability by adding a conflicting edge.
No, so okay. So suppose you are given a matching, and somebody claims that it is stable, and you want to contradict him or her. How will you contradict him or her? Or you want to show that that person is wrong. How will you show that?
So that is, if there exists a particular edge like that has better priorities for both of them. Like,
excellent. So we want to show that there is a blocking pair, right? That is a pair which is unstable. Both of the endpoints prefer each other to their current partners. So what we have is this A1, B1, A2, B2 is a stable matching, which we have claimed for the sake of contradiction, which is a larger size matching, and which gives us a 3-length augmenting path. Can we try to show that this matching is unstable, and the only handle that we seem to have is about this edge A2, B1, which is not present in the gray matching and is an edge in the graph, because if it were not an edge in the graph, our matching could not have matched it. So if this is the situation, we want to show that A2, B1 is a blocking pair or an unstable pair with respect to the matching. To show that, we have to show that A2 strictly prefers B1 over B2, and B1 also strictly prefers A2 over A1. And this strict is important because remember that there are ties in B's preference list. That is, the women can have ties in the preferences. So let's make the observations. So now use our observations. So remember that after doing all our algorithm, we have that B2 is unmatched, right? If B2 were not unmatched, we would have drawn a red edge incident on it and continued this path. Then it would not have been a 3-length augmenting path, and therefore we would have continued. So therefore B2 is unmatched after doing all this Kiraya's algorithm, that is Gale and Shapley, then men propose with increased priority and so on. So it means that B2 never received a proposal from anybody, and in particular from A2. So A2 has never proposed to B2, because we said that if a woman remains unmatched after our algorithm, she never received a proposal. So she never received a proposal from A2, and therefore A2 must strictly prefer B1 over B2, because A2 is going in its order and proposing the women in the preference list. So therefore A2 must strictly prefer A2 must strictly prefer B1 over B2. In addition, A2 did not get increased priority. So how did I conclude this, that it did not get increased priority?
Yeah, variation 2 would apply if it was increased priority, right?
Sorry.
Variation 2 would apply if it had increased priority.
Yes, we would apply increased priority. See, if somebody has gotten an increased priority, that person has proposed to everybody in the preference list in the first round, right? But we have already agreed that A2 has never proposed to B2, because B2 never received a proposal. So therefore A2 cannot claim that, or
yes, Dimple? Okay, thanks.
Yeah, so A2 has never proposed, A2 has never even finished its preference list in the first round of Gale and Shapley. So therefore, we cannot say that A2, A2 cannot get increased priority, and therefore A2 strictly prefers B1 over B2. So half the part of our proof is done. That is, we know that A2 strictly prefers B1 over B2. Now is the second part, where we need to show that B1 also strictly prefers A2 over A1. If we do that, then we have a blocking pair. So what do we know? A1 is unmatched at the end of the algorithm, and if a man is unmatched, it must have got increased priority by our algorithm. Note that our algorithm has executed, so it must have got increased priority, and with increased priority, it must have proposed to everybody in the preference list. So what happened when A1 proposed to B1 with increased priority? If it were in a tie with A2, then A2 does not have high priority. Therefore, B1 would have accepted the proposal from A1, and A1 would have been a red edge. But this did not happen, which means that B1 strictly prefers A2 over A1. So this is important, that we have established that A2 did not get increased priority. Therefore, A2 is at the normal priority or without a star, and A1 is a vertex or a man with a increased priority or star. So if a starred man proposes, and if B1 has a tie between A1 and A2, then it would have been the case that it would have accepted A1 over A2. But since this did not happen, it must be the case that B1 strictly prefers A2 over A1, and therefore we have established both the things required to show that A2B1 forms a blocking pair with respect to the gray edges, which were supposed to be a stable matching pair of edges in the original graph. So this pair is a blocking pair with respect to the supposed gray edges, which are a part of a stable matching, which contradicts that the gray edges form a stable matching in the original graph, and therefore such a 3-length augmenting path cannot exist. So is this proof clear? The proof very crucially uses the fact that we have run the Kiraya's algorithm, B2 is unmatched, A1 is unmatched at the end of it, and the properties of these two vertices. So any questions or queries? Okay, so what we have established by this is that the output of our algorithm does not have a 1-length augmenting path, neither does it have a 3-length augmenting path. Therefore, it is size, which is at least 2 over 3, which is the same thing as k over k plus 1, which we established, the size of the maximum cardinality stable matching in the instance. and therefore we have an approximation to the maximum cardinality weakly stable matching. I interchangeably use the word weakly stable, but in this context it is just stable. Okay, so assuming that this this is clear or semi-clear, I should say, we will move on to the next thing, and I just want to recap. So what we have done is we have done this Kiraya's algorithm, which is 2/3 approximation to the maximum cardinalities matching. And what we see is that it's a simple extension of the Galen-Shapley algorithm, and this very useful idea of increased priorities, which we are going to revisit in the second variant that we are going to look at. I mean, second, or in fact, the first variant that we have proposed, and we are going to look at that. Okay, so this is the summary of what we have done till now, and now we are going to focus on variation 1, where we have strict and incomplete lists, and our goal is to compute an optimal matching of larger size. So I'll just go back a few slides and recall why did we say this, if anybody has forgotten. So so there was this variation 1 where we said that yeah, so I recall the fact that we do have a stable matching. Every stable matching matches the same is having the same size. However, stable matchings can be half the size of the maximum cardinality matching. And are there larger size matchings which are optimal? And we said that if we want to have larger size matchings, we have to, I mean, forego or give up stability, because all stable matchings have the same size. So in this variation where we have incomplete lists, but they are all strict, we cannot hope to get different size stable matchings like we had, but we will have to forego stability. So we are going to introduce a new notion of optimality and say that we are going to compute matchings which are optimal according to that criteria, and they will, I mean, they will still be of use, and we'll see how. So what we are going to define is the notion of what we call as popularity. And this notion has been introduced long ago in 1975 by Gardenforth. And it allows us to compare two matchings using the votes of the participants. So this is a different notion. You can start paying attention if you have missed out some of the things. So, so let's look at our standard example. We have two matchings shown now. So the first matching, which I call as the red matching, is shown using the circle. So it is A1, B1, which is listed here. We also know that in this instance, it is a stable matching. We also have given another matching, which is A2, B1. So that is also of size 1. We also know that there is a two-sized matching in this instance, but just to illustrate this thing, we are showing it using two matchings, M and MS, which are of the same size, which are of size 1. And what do I mean by these votes? So let's do this table. So we have just 3 people voting, and we'll see why. So A1, A2, B1, I should have written B2. I don't, yeah. So B2 is not there because B2 remains unmatched in both the matching. So it doesn't care what happens, which matching does the central authority choose. Both of them are equally good or equally bad for it. So let's look at A1. A1 says I get B1 here versus I remain unmatched in the blue matching. So I will give my vote to MS, or the red matching. A2 says I do not get anything in the red matching. So I will give my vote to M. B1 says I am matched in both of them, but I get a better partner in the red matching. So I am going to give my vote to MS. So therefore now you have completed this table. This table is tedious, but it can be easily done. And once you have computed this table, you just ask which matching gets more votes over the other. And the one which gets more votes will be called as a more popular matching. That is, it is better in terms of popularity, better in terms of this notion of popularity with respect to the other matching. So it's only a pairwise comparison, and a matching is popular if it cannot be beaten by any other matching. So if you take a matching and show that some other matching doesn't beat it, doesn't mean that that matching has become popular. You have to make sure that no other matching beats it. On the other hand, to show that some matching is not popular, it is easy. You just have to show one matching that beats it with respect to popularity. Similar to what we did in stable matchings, if you give me a matching which you claim to be stable, I will have to check for every unmatched edge, does it block that matching. If I show you one unmatched edge which blocks the matching, it's not stable. But to prove that it is a stable matching, you have to make sure that every unmatched edge doesn't block it. Similarly, to show that a matching is popular, you have to do it for all the matchings. The difference here is that there are exponentially many matchings. The number of edges that we had to check was not exponential. So, just, I mean, defining this is easy, but saying whether a matching is popular or not is not going to be as easy. So the question is, does a popular matching exist? Fortunately, the answer is yes. Every stable matching is a popular matching. Therefore, it is good that we have at least there is an existence of the matching. However, there can be larger sized popular matchings that need not be stable. So let's view this in the same example, but with different matchings. So our MS, that is the red matching, remains the same. This is A1, B1, but the blue matching changes. The blue matching has A1 match to B2 and A2 match to B1. This also we know by now. This is the two-sized matching that is there. The instance is very small. There is nothing much to do. But now if we look at the votes, let's look at the votes. We know that A1, of course, it gets its top choice, so it's going to give it to the red matching. It now remains matched in the other matching also, but it gets its second choice. A2, of course, it doesn't get matched here, so it will give its vote to the blue matching. B1 again keeps its vote with MS, but B2 also starts voting, and B2 says that now I like the blue matching because I get matched versus remaining unmatched. So with respect to these two matchings, MS and M, neither of them beats the other because the votes just cancel out. So is this a definition clear to everybody? How are we voting? Any questions here?
What did we conclude when they're equal?
We are just concluding that neither of them is more popular than the other.
Okay. Ma'am, can there be a case where like the outcomes are the same? You just vote for both of them?
Outcomes are the same, meaning?
Meaning like it gets matched to the same priority in both the matchings. So
okay, let's add another A3 and put a B3 here and say that A3 B3 gets matched in both MS and M prime. What do you think? What is A3's role? What does it do? We can either let it give vote to both of them or not give a vote at all. So we take this route. It is equivalent, right? Because you are adding one to both of them or not adding one. So doesn't matter. So whichever stand you want to take, that is fine. But you have to take it consistently. That is, it will always vote for both of them or not vote. So we take the stand that such people or such participants do not vote between the matchings.
Okay, because their votes do not matter.
Yeah, their votes do not matter, right? Yeah, great. Yeah. So A3, B3 both vote.
Like ma'am, if suppose A1 in A1's list, both B1 and B2, if they are tied, then A1 will vote for which matching?
Then again, we can define votes. We can say that A1 and B1 are both A1 is indifferent between B1 and B2, in which case it doesn't vote, or it votes for both the way you want to choose, but it doesn't vote for any of them. That is what we will choose. But remember that we are looking at the case where there are strict lists and incomplete lists.
Oh, okay. Thank you.
Right? Thank you. We won't get into this situation in this variant, but this is a valid question.
So, ma'am, so to break a tie in between M red and M blue, all it requires is one instance of indifference, right?
I did not understand. So
No, so now choosing between the red and blue matching finally would mean that to break the tie, we just require one instance of indifference.
I don't know what.
So suppose
Example, yeah, in this example, one instance of indifference will work. But in general, you have seen this, right? I mean, in the earlier example, there was no indifference, but still MS is better than M because
yes, here it is clear because there are 2 votes to 1. But when the votes are same, to break the tie, I would require someone to become indifferent.
No. So we don't take that route. We never change the preferences of the participants.
Okay.
We will say that both MS and M are equally popular. There can be multiple popular matchings in an
Okay.
Just like we have seen that there are multiple stable matchings, there can be multiple popular matchings also. So we don't change preferences of participants at all. Okay.
And ma'am, if suppose if we have multiple popular matchings, so will the size of each matching will be same or different?
No. So popular matchings do not enjoy the property that they have the same size. In fact, the stable matching is popular, and we will show that in this instance M prime is also popular. So you already see, if you believe me for a moment, that MS, and in fact there is not too much work to do, right? So what did I say as the definition of popularity? That a matching is popular if it cannot be beaten by any other matching. So if the only other non-trivial matching is M that we had shown in the previous slide, that is beaten by MS, so that cannot be popular, and the empty matching cannot beat anybody else. So therefore these 2 matchings are indeed popular, and they do not have the same size. So popular matchings do not have the same size, and therefore the natural goal is, can you compute a maximum cardinality popular matching? Okay, so I repeat that by showing that 2 matchings are equal in terms of their votes does not prove that it is one of them is popular. It just says that this doesn't give you any conclusive answer. On the other hand, to show that a matching is not popular, it suffices to give one matching which beats the others and beats that matching in terms of the votes. Okay, so what is our goal? Our goal is to compute in this instance. So remember, we have strict and incomplete list. Our goal is to compute in this instance a matching that is maximum cardinality and maximum cardinality popular. So it need not be the largest size in the instance, but it is the matching which is popular, and amongst all the popular matchings it has the largest size. And the stable matching, if it is stable matchings which always exist, are always an answer because they are that is a popular matching. We haven't shown that. If I get time, I will show that. Okay, so yeah, so just in fact, in this example, we have claimed that M prime is a popular matching, and our goal is to compute a popular matching in this instance. Note that this variant is also very different from the variant that we saw earlier where there were ties, and the goal is also different. It was an NP-hard problem. Our goal was to compute an approximation to the maximum size stable matching, and here the goal is to compute a popular matching. However, the same idea, a small tweak or a difference in that idea works here also, and we will show how it works. Okay, so this result is due to Kavita. It was published in 2012, and the result, the algorithm is very similar to what we have seen, and that is why I decided to present it together. So it says run the Gale-Shapley algorithm. Remember, there is no break ties arbitrarily because there are no ties at all. So run the Gale-Shapley algorithm. Then unmatched A's, if there is an unmatched A, proposes with increased priority. And remember, in the earlier case of Kiraya, when unmatched A proposed with increased priority, the B's decided to accept or reject it based on ties in their preferences. But here there are no ties. So whenever we get an increased priority proposal, the person is going to accept it. But if you get 2 increased priority, that is, you are currently matched to a man A star, and you get a proposal from A prime star, then you will look at your original preference list and ask, okay, which one do I prefer between the 2? in the original preference list, and you will use your original preference list to decide the preference. So between 2 star men, you use your regular preference. Between 2 unstarred men, you use your regular preference. Between a star and an unstarred man, the women will always accept the starred person, right? So we will again execute the algorithm on this instance. And as we know, we have agreed that stability can be violated because now we are allowing men to be accepted even out of order. So therefore stability can be violated. However, the guarantees of this algorithm are that it will produce a popular matching. It will in fact be a matching which has size at least the size of the stable matching, and it will be 2/3 the size of a maximum cardinality matching in the instance. This proof is very similar to what we did earlier, and it is of course a linear time algorithm. So I would yeah, at this point, is there any question? Because I'm going to switch my this thing and go to my Jamboard and then start writing, hopefully, which you will be able to see. So yeah, I'll wait for a second and then I'll stop sharing this and start sharing my Jamboard. So I would like to recall our preferences. That is, we had A1, which is having B1, B2, and A2, which is having B1. And we have B1, which is having A1, A2, and B2, which is having A1, right? So now when we run this algorithm, we know what stable matching does. So we are going to, I'm just going to write this down. So we know that the stable matching is A1, B1. So this is the stable matching. At this stage, we know that A2 is unmatched. Therefore, A2 is going to start proposing with higher priority. So what does A2 do? A2 star proposes to the only person in its preference list, which is B1. At this stage, B1 has accepted A1 tentatively, but it gets a proposal from a higher priority man. Therefore, it is going to reject this A1's proposal and accept the proposal of A2 star, and therefore A1 becomes unmatched. This is very similar to what is happening, but remember there are no ties in B1's preference list, yet it is accepting that. And now A1 goes ahead and proposes to B2 because it is not even finished its preference list with regular priority, and therefore we get the matching which is shown here on the top, which is A2 is matched to B1 and A1 is matched to B2. So this matching that I am highlighting is the one that we get. So why have I highlight? I mean, the matched edges are, as you see, are in the wiggly edges, but I have also shown this edge, which is a red edge, which is between A1, B1, and that is a unstable edge or a blocking edge or an unstable pair, because A1 prefers B1 over its current partner, and B1 also prefers A1 over its current partner, which is A2. So it is an unstable pair. We are going to live with these and still claim that the matching is popular. So in some way, stability says that no pair has incentive to deviate. So you cannot allow such blocking pairs in stable matchings. You will allow these blocking pairs in unstable, in popular matchings, but say that no majority of the participants want to deviate. So this is the difference between stability and popularity, right? Okay, so what I'm going to do, so is there any question about this? Okay, so what I'm going to do is, I'm going to now, the way we made some observations about Kiraya's algorithm, I'm going to make observations about the men, the way we can partition the men and women in our bipartite graph with respect to the algorithm. So remember that our algorithm has run the Gale and Shapley and then run the increased priority proposal sequence also. So what we will do is we will partition the men as the men that we have as A1 and A0, and the women as B1 and B0. And the way we will partition them is as follows. That is, A1 is the set of men who got a star status. That is, they increase their priority. Remember that with increased priority also, they may not get matched. That is not guaranteed that with increased priority you will get matched. but you have got an increased priority, and therefore you may be matched, but you may also not be unmatched. So can somebody think of a simple case where with increased priority you do not get matched? Is there a simple example that you can think of? Okay, so I'm going to write this example in the right side of the board. So it is A1, A2. Both of them have just B1 as their top choice, and B1 has A1 alone. That is all is the instance. I hope everybody can see this instance. Now, what happens with our algorithm? So the proposal sequence goes as follows: A1, B1, A2, B1. So A1, B1 gets accepted, A2, B1 gets rejected. At this, we will give A2 a higher priority. So A2 will say that A2 star is going to propose to B1. It will get accepted. A1 remains unmatched because A1 does not have anybody to propose to. But we are not going to treat A1 unfairly. A1 also will get a star status, and A1 will propose to B1. At this stage, B1 will say, okay, now I don't care between for your star status, because I have got the proposal from A1 with a star status. So I will reject this proposal and accept it. So what we get is A1 star B1, which was our original stable matching. So it is not guaranteed that always we will increase the size, because there may not be anything to increase the size. And note that in this instance, matching A2 to B1 is not a popular matching, because that is not popular in fact. So you cannot match A2 to B1, but you will have to match A1 to B1. So therefore, in fact, this answer is correct, and you should give this increased priority to both of them. So any questions or comments here? Okay, so now what we understand is that we have the set of men, we have divided them, or we have called the men who got increased priority as being in the set A1, and the men who are remaining or who did not get the increased priority in A0. So, so what I want to ask is, where are the unmatched men? Where can the unmatched men lie? So there may be some unmatched men at the end of the algorithm. Where will they lie if they have to lie between these partitions? Any idea, any thought? Can they lie in B0? B0 or B1? I mean, I don't know whether, I mean, is it that class has lost me, or what is it? I mean, people are completely clueless about what is going on. Okay, so somebody has to say something, otherwise I don't know whether anything is going on. So I want somebody to tell where is the set of unmatched men, or where, suppose there is a man which is unmatched, where will it lie in this partition, A1 and A0?
Yes, Meghana in the chat.
Oh, sorry, I did not see.
A1. A1.
Okay. Yeah, so somebody has said A1, is it? Okay. So why is it in A1? Why do you say that it is in A1? Oh, so I think Pratisha and the TAs are answering. Thanks, Pratisha. But yeah, I don't know whether the participants have lost me completely. Okay, so anyway, I'll complete the proof. So the reason that unmatched men cannot lie in A0 is, if a man was unmatched, then the man must have got an increased priority, and therefore it must have gone to the higher level. So we have already said that the set of men who got star status are present in A1. Therefore, if there is an unmatched man, it must lie in A1. So all the men in A0 have matched partners, right? And what we will call B1 is the set of women who are matched to men in A1, right? So again, There can be unmatched women. We have not told what we'll do with them, but these women in B1 are the ones that are matched to men in A1. Therefore, again, by the definition, unmatched women cannot lie in B1. So unmatched women, if it is there, it must lie in B0, and that is again by definition. So the unmatched women will lie in B0, unmatched men will lie in A1. Right? So this is the situation, and we have decided B0 is equal to B minus B1. So this is the way we have partitioned. So every man and woman has a place in this partition. It lies either in A1 or A0 and B1 or B0, right? The men are A's and women are B's. Okay, very good. So now what we want to do is we want to look at these edges and ask how are the edges which are matched edges versus unmatched edges. So note that all the matched edges that we have, by definition, again, they are going to be horizontal, or they will lie completely in A1, B1 or in A0, B0. So why do I say this? Because I have said that for every the way I have selected the B1s is the set of women which are matched partners of A1s, right? So therefore, I have selected these edges to become horizontal by design, and these edges as a consequence are going to be horizontal, because I will never put a woman whose partner is in A0 in B1. That is how I have designed my sets B1 and B0. Therefore, by design, the matched edges are going to be horizontal. So the blue edges are always going to be matched edges for us. Now, unmatched edges, how can they look like? They can be all over the place. So they can be, so I'm going to draw these unmatched edges with black, and they can be here. So this is an unmatched edge. This can be an unmatched edge. They can have their matched partners. There can be unmatched edges completely belonging to A0, B0, or they can go across. They can also be like this. So they can be all over, and I do not know how they are. But now we will analyze these edges. So what we are doing first is we are going to take these edges which are unmatched edges, which are, I have drawn them as green edges, and I want to analyze these edges and ask how do they behave in terms of the votes that they get. Okay, sorry, so I have not changed my view. Okay, so I am going to look at this unmatched edges which I have drawn in green, and I want to analyze these. These are edges from A1 to B0, and I want to analyze them. So I've written these edges as A0, B1 edges. Now my claim is that these edges are actually the edges where both the endpoints prefer their M partners, which I have called them respectively as MA and MB, because I have chosen this edge as AB. I want to say that they both prefer their M partners over each other. Now let's see why this happens. So let's look at this vertex A and ask, does it prefer its M partner over this B? So what has happened during the course of the algorithm? It received a star status, and it went to, that is why we are having it in A1, and it received a star status and started proposing. So it proposes in the order in its preference list. Therefore, there is no way it violates its ordering. So when it proposed if it preferred B over its matched partner, then it would have proposed to B, and B being matched to a lower priority man, it would have accepted the proposal. So since this did not happen, it means that A prefers its matched partner over over B. Similarly, when we look at B, we ask what happened during the proposal sequence of Gale and Shapley itself. A must have proposed to everybody, and A must have been rejected by B also, and that is why it went to a star status. Therefore, we know that B also must be preferring its matched partner over A. Therefore, both these are actually preferring their matched partners over A, and in fact this green is indicative that this edge is a good edge for M, because if another matching has this edge, then the votes of A and B are going to the blue matching versus the green matching, because that green matching, those people do not like their partner. I mean, A does not like B over its matched partner. B does not like A over its blue partner. So therefore, these green edges are good for our matching or the blue matching. On the other hand, let's look at these edges, that is of the form which is A0 to B1. And now you should observe. So I'll go a few. Okay, so I did not change your view, sorry. So let's look at these edges, which is A0 to B1. And these edges, in fact, as we have seen in our example earlier, so in the first example that we had drawn, we had seen that this edge that I am going to highlight is a bad edge. That is, if somebody takes this edge in another matching, then both A1 and B1 like each other over their current partners, right? So therefore, this is a red or a bad edge for the matching that we have constructed. So to summarize, I mean, visually summarize, what we are saying is that there are these green edges which are good for our matching. There are these black edges, red edges, which are bad for our matching. So the A1 B0 edges are good. The A0 B1 edges are bad for our matching. Now, what we want to say is, what are the other edges? The other edges can be between the completely contained inside A1 B1 or A0 B0. But these edges cannot be bad. These edges cannot be bad. They can be plus minus. That is, one endpoint likes one match, the match partner. The other endpoint likes the other endpoint likes that pair with respect to the matched partner. But it cannot be an edge where both the endpoints prefer each other to their current partners. Why? Because the Gale and Shapley proposals were followed when we looked at how the A's proposed during the first round and how the A's proposed during the increased priority round. So when the increased priority happened, if there were two people with increased priority, the B looked at its own preference list and then simply used that priority. So therefore, if an edge, unmatched edge, is completely contained inside A1 B1 or between A0 B0, it's a safe edge. It is not a harmful edge. The red edges are bad because M loses 2 votes. The green edges are good because if somebody uses that edge, then we gain 2 votes. That is, the blue matching gets 2 votes for us. So is this classification clear? We are just nearing the proof, so don't worry about the time. Okay, so again, I'll assume that it is fine. So now recall that we had already seen this, seen our thing about so we had already seen this thing about the symmetric difference of M and N. So if we want to show that M produced by our algorithm is popular, then we want to claim that there does not exist a matching N that gets more votes over M. And to do this, what we are going to do is again look at the symmetric difference of M and N. And the symmetric difference of M and N, we know that it contains these paths and cycles. And now remember that it's not a maximum cardinality matching. You actually can have augmenting paths with respect to M, alternating paths with respect to M, and so on. So you can have all sorts of structure. In particular, you can have cycles, but whenever there are cycles, it has even length because it is the graph on the symmetric difference. Now, if N gets more votes, that is, if M is not popular, then N gets more votes. Then N must get more votes along one of these components, that is the components that we have drawn in the symmetric difference. So let's analyze one of these components, in particular the cycle. And how does this cycle look like? So if the cycle completely belongs to this A1 B1, then the cycle consists of only unmatched edges which are harmless edges, or which are containing either one vote on the other side, one vote for M, the other vote for N. So if it completely contained inside the A1 B1 part or A0 B0 part, we are safe because we don't have anything to worry. The only case where we have to worry is if it uses this B1 A0 or A1 B0 edge, right? So I would like us to see how do we draw this, how do we collect large number of these edges. If we want to collect large number of these edges, which is of this form, what I am going to now try to draw this cycle. So let me say that if I start with something which is A1, B1 edge, which is a blue edge, which is a matched edge. So this is how I start my cycle. Then let me say that I do want to take a bad edge, that is this B1 A0 edge. So I will take a unmatched edge, which goes here. Now after this, what can I do? I have to be in B0, because the matched partner of A0 does not lie in B1. So I cannot simply go to B1. So I must lie here. So I must take a blue edge here. Okay, great. So I took this blue edge. Now, one way is I can go from B0 to A1, which is fine. But then if I take this, it is a green edge. That is, it is a good edge for us. So I have lost 2 votes along this edge. That is, my adversary has created a bad situation for me. But as soon as you want to create further bad situation for me, you must first correct the bad situation. That is, you must first get a good edge and then go towards a bad situation again. So let's say that the cycle continues again here in the part which is below. Then there is no harm that happens, and we simply, are with, no extra votes against M that we have collected. Now maybe we decide to go to A1, in which case we must pick up this green edge. So we must pick up this, which means that whatever bad that the adversary had created for me by using this red edge has been now nullified by this green edge. And now I can again go for a long time in A1, B1, and then come back again to A0. But again, that is a fresh bad thing that you have created for me, which is not adding to the old votes that you had collected for yourself. So therefore, as soon as you create one bad edge for me, I will force you to create another good edge for me before you collect more bad edges. So this is the overall line of proof that we have, which tells us that the matching N, and again, I have just taken one cycle and argued about it. You have to argue about it for all of these structures, but in the interest of time, I'm not going to do that. So for each of these structures, it can be argued that you cannot create more bad edges than the number of good edges. Therefore, the number of votes will compensate, and therefore the matching that you have produced is popular. It requires some more work to show that it is a maximum cardinality popular matching, but I will leave that in the interest of time. I'm just going to go back to my slides and summarize the discussion. So what we have seen in the lectures spanning yesterday and today is the classical variant of the stable matching problem. Then I'll correct this in my slides. It is incomplete lists and ties, and in that we have seen computing the largest stable matching. This algorithm is by Kiraya, and the idea of increased priority, which allows us to get a good approximation to the maximum cardinality stable matching in the instance. And this idea has been used later in Kavita's work, where she has used this to it's a different proof, and it's a completely it's a very nice thing that this idea could be used for computing popular matchings. And later on, we have used this idea to compute popular matchings under different conditions, which is called as in the presence of lower quotas, which is again interesting. So that is a follow-up work of this line of work. So what I want to emphasize is that this very simple idea of giving increased priority has turned out to be a very useful thing that that has applications in several places. So the main takeaway is that whenever you're designing your algorithms, try to be as simple as possible, and that may lead to elegant and nicely designed algorithms. So with this, I'll stop the discussion, and yeah, these are some of the things that In all the cases, these algorithms can be written as a reduction to a suitable stable marriage instance, where you can simply run the Gale and Shapley algorithm and produce the output. And it also works in the presence of capacities or upper quotas, which we did not have time to discuss. So with this, I thank all of you for your participation. I thank once again the organizers for inviting me and giving this opportunity to talk to speak to you in the school. So thanks all. If there are questions, I'll be happy to take them.
Meghana, what are the variants that are being studied right now in literature? I mean, the big open questions in matching.
Okay, in general or related to this?
With respect, related to this.
Okay, so so as I mentioned in the previous yesterday's class also, and somebody had asked me, so this is not the correct picture. There is a slightly modified picture. So yeah, so you see this here, right? So this is the strict list, this is the incomplete list and ties, and again we are talking only about ties on B side, but the general case of ties on both sides is also studied. There is a gap in the approximation. This red denotes that it is the lower bound, that is there's no known, you cannot approximate it below 0.9, but the current this thing is 0.73, and the improvement is happening, as I said, with lot of efforts, with new techniques being used. This algorithm uses an LP and so on to do the rounding. So computing largest size maximum, computing a good approximation to the maximum size stable matching, that is one this thing. Then the idea of in terms of the capacities, when you have capacities, then it introduces different challenges. One of the things that we are considering is introducing lower quotas. That is, you also have that there are demands on vertices, and one of the works we have done this for lower quotas. Extending these things to in the presence of capacities or in the many to many setting is also something which is an interesting challenge. Some of the things come up or can work out easily in the one-to-one setting, but or with less effort, but making them work for the many-to-many setting is an interesting challenge.
Okay. And how are these algorithms? Has anybody studied this experimentally? Like practically?
Yes.
Because it's a very, you can think of 100 applications for this question at any moment, right?
Yes. Yeah, so people have studied Byro and Manlove and others. They have an experimental evaluation of especially this the computing maximum cardinality stable matchings in the case of incomplete lists and ties. And in fact, Kiraya's algorithm does quite well in that context. But there are other algorithms also. In some cases, so they do it on real world as well as synthetically generated data sets. And there is an experimental paper on this. So I will point out to the links to these things that you have asked me.
Okay.
Yeah, and we also did our experiments. We also have implemented some of these algorithms, and we are also trying to build a portal where these algorithms can be used by others.
Okay, good. Any other question?
Thank you, Professor Meghana, for
there is a, I'm sorry, Avi. There is a question in the chat.
Okay, sure. I will
can you see it or?
Yeah, if you, I think I'll be able to see it. Just a minute. So with the ties, there are hardness results known for deciding whether there is a popular matching. in the instance. So that is the question, right, Sachin?
Thank you, ma'am, for lecture on stable matching, and this was an interesting lecture. We will have our last session on dynamic algorithm by Professor Manoj Gupta at 2:30 p.m. See you all there. Thank you.